All right, welcome back, everybody. So we are going to be jumping into this investigating infinite series set of notes, which is going to be similar to where we ended the notes off last time in talking about series. So we're going to start with just a few examples to kind of get started. And this is going to be an important idea in connecting the derivatives with a function with the equation of a function. So in other words, the derivatives of a function determine the coefficients of a function, which is going to be kind of interesting. So let's start with number one. So suppose a cubic polynomial has these following derivatives. So f of 0 is 1, f prime of 0 is 4, f double prime of 0 is 8, f triple prime of 0 is 12. The question is, what is f of x? So we know it's cubic, right? So we can note that f of x is going to look like ax cubed plus bx squared plus cx plus d, just using kind of a standard form representation. So if we look at these values, we can clearly see the derivatives are going to be important. So instead of maybe plugging in f of 0 equals 1 to start, let's just take all of our derivatives first and then consider our values. So we'll have f prime of x is going to be 3ax squared plus 2bx plus c. F double prime is going to be 6ax plus 2b. And then f triple prime is going to equal 6a. And now we can use our given values kind of in reverse, right? Starting with our f triple prime of 0 is equal to 12. Obviously, the 0 doesn't matter here because there's no x value. So our third derivative doesn't depend upon x. So we'll get that f triple prime of 0 is equal to 6a, which is also equal to 12. So obviously a is equal to 2. Okay. And now we can go to our second derivative. All right. So we're going to get f double prime of 0 is, now 6a is 6 times 2, which we just found. So that's going to be 12. But it's times 0, right? So note, we don't really need to substitute back in because x is 0 here. So it's actually going to be the nicest of all cases. Plus 2b, but we know that that's equal to 8, which means b is equal to 4. And then for f prime, again, we can ignore the x terms because they're going to be 0. So we'll get c, which is equal to 4. And then our last one is just going to give us that d is equal to 1, because all of our terms are 0. So that means that our function, which maybe I'll write up at the top here since I'm running out of space, f of x is equal to 2x cubed plus 4x squared plus 4x plus 1. And all of those values, 1, 4, 8, and 12 of our derivative, come directly from the application of the derivative here. Right? So if I take my 2x cubed term and I differentiate it over and over and over again, I get 2 times 3 x squared. And then if I differentiate that, I get 2. And then 1 going all the way down to a constant, which gives me 12. So this would be, again, from f prime, f double prime, and f triple prime. So as we differentiate and use this power rule, right, there's this multiplier effect that occurs with each derivative in the coefficient. All right, so again, we'll discuss this in more detail. Whoops, we'll leave that up. All right, so for number 2, this is a quartic polynomial. So now it's going to be a degree 5 one. I will let you do this one on your own. So it's going to work out very similarly. And what you will notice, right, is that those coefficients are going to really matter the same way. So what I do want to get to, though, is number 3. So we're going to let f of x be this 5th degree polynomial. And so let's quickly find the first 5 derivatives at x equals 0. So we'll note f of 0 is 2, f prime of 0. So everything's going to become 0, and the only thing that's left is 3. And maybe we'll write the f primes up here. So f prime of x is going to be 3 plus 4 times 2x plus 5 times 3x squared plus 6 times 4x cubed plus 7 times 5 x to the 4th. And I'm going to write it this particular way where I'm kind of leaving the coefficient unmultiplied, just so we can kind of see what the pattern is going to look like. So obviously at 0, we're just going to end up with 3. And then for f double prime of 0, so f double prime, we're going to get 8 plus 5 times 3 times 2x plus 6 times 4 times 3 plus 7 times 5 times 4 x cubed. And note this 8 is really 4 times 2 times 1, where this 2 times 1 we'll just notice is 2 factorial. And this 3 times 2 is really 3 factorial. And this 4 times 3 is not quite 4 factorial because I don't have a 2 there, but I'm going to have a 2 there. So there's this factorial behavior going on in the background here. So we'll get 8. So for f triple prime of 0, we're going to get 5 times 3 factorial, so 3 times 2 times 1, plus 6 times 4 factorial. And we'll note here that we had 1 factorial with the 3 and 2 factorial with the 4 times 2. So with that 8. So we've got 1 factorial, 2 factorial, 3 factorial, 4 factorial. For 7, we're almost to 5 factorial. But no, we haven't canceled enough terms yet. We still need to bring that 2 down. So this is really 5 times 6, which is just 30. For the 4th derivative, so note once we go higher than 3 derivatives, we can just start using actual numbers instead of tick marks or apostrophes. So the 4th derivative at 0 is going to equal, so 6 times 4 factorial, which is 6 times 24. So that's going to be 144. Yeah, that's going to be 144. And then we've got 7 times 5 factorial. All right. And so for the 5th derivative, that's going to be 7 times 5 factorial. So that's going to be a big number. 5 factorial is 120 times 7 is going to be 700 plus 140, so I think 840. Maybe double check me on that. So 700 plus 140, I think, gives us 840. And so we get our quick derivatives here. But what we can notice here is that f of 0 was really 2 times 0 factorial. F prime of 0 is the same as 3 times 1 factorial. F double prime of 0 was 4 times 2 factorial. F triple prime of 0 was 5 times 3 factorial. And the fourth derivative at 0 was 6 times 4 factorial. Was 7 times 5 factorial. And note, I picked the coefficients, obviously, to be 2, 3, 4, 5, 6, and 7 in our original polynomial. So we can see that whatever our coefficient was, so if it wasn't 2, 3, 4, 5, 6, 7, it would just be the initial coefficient times n factorial, where n is the derivative, right? So if I had Fn, so the nth derivative at 0, that's going to be our coefficient at n, so whatever c sub n is, times n factorial. And what that means then is that the coefficient n, so note this is the coefficient of the nth term of the polynomial. C sub n is equal to the nth derivative at 0 all over n factorial. So what that means is that the coefficients of your polynomial are simply going to look like the ratio of the derivative, the nth derivative, so the derivative that's matching. So it's the number of derivatives you need to make whichever term you're looking at a constant, right? So if I'm looking at the x cubed term, I need to differentiate x cubed 3 times in order for the x to disappear. So the third derivative would be needed to get rid of the x cubed. So if I want to know the coefficient there, all I need to look at is what is the derivative applied 3 times, in this case at 0, all over the factorial, which is just the number of the power that I started with. So note, this represents any term. And what this means is that every polynomial, which kind of should be obvious, is completely determinable by its derivatives. So as I put down here, there's nothing special about this polynomial, and the power rule applies regardless. Therefore, this is true for every polynomial function. So what this is going to mean in particular then is that this nth derivative at 0 over n factorial is equal to our coefficient n. And this has a special name, which we're going to explore more. And this is the Taylor coefficient. Now, the one thing that is going to be kind of special to this is that we are finding the values at 0. So we're finding the values at 0 is very specific to this example. We're not always going to be finding values at 0. So finding values at 0 actually makes this what we call a Maclaurin series value, but we haven't quite gotten there yet. All right, so for this first part of the notes, again, we're just using the derivatives to try and make connections between the coefficients and the actual derivative itself. Okay, so this is just kind of our starting point. So we'll pause here, and then we'll come back and we'll look at that geometric series that we discussed in the last set of notes. So if you have questions, shoot me an email. Otherwise, come by the office hours. So until I see you next time.